Hello, my name is Theodore C. Noonmaker. I'm in grade 6 at the Plains Intermediate School in Athens County, Ohio. So, my experiment was it's the prime time to find the primes, creating an equation to predict prime numbers. So what actually is a prime number? Well, prime numbers are defined as any number that has only two factors, one and itself. They may be related to biology, and they have a major use in forms of cryptography. So as for prime numbers in biology, they could have a role in the life cycle of periodical cicadas, these cute little guys. So they emerge every 13 or 17 years, and 13 and 17 are both prime numbers. This may happen so that the cicada's life cycles are sort of out of sync with the life cycles of other animals like predators, and this could increase the cicada's chances of survival. Now, as for prime numbers in cryptography, they do have a major use in a form of cryptography called the RSA method. It was created by three mathematicians named Ron Rivest, Adi Shamir, and Leonard Edelman. So basically what it does is it uses really advanced methods, but what it really does is it uses prime numbers to encrypt your messages, send them to someone, and decrypt those messages so that that person you sent them to can actually read them. And then, since prime numbers only have two factors, they're pretty hard to track, which makes them useful so that hackers can't hack your messages. And so, just prime numbers play a huge role in this, and they just keep your messages safe, which is really what cryptography is all about. So now you can see that prime numbers definitely are useful, but they get hard to find and confirm as they get larger. So due to this, people have come up with many ways of finding prime numbers easier. Here are two of them. So one of the ways is reflected in a current organization known as the Great Internet Mersenne Prime Search, or GIMPS for short. And really what that is it's an ongoing organization dedicated to finding Mersenne primes. Now, Mersenne primes are prime numbers that can be represented in the form 2 to the p minus 1 power. The point of just finding these prime numbers is to ensure that any prime numbers found will be very large. And it works pretty well because I think the fifth Mersenne prime number is already in like the thousands. So they get very large very quickly. The next is the sieve of Eratosthenes, and basically what this is it's just a mathematical statement that helps to narrow down what numbers can be prime. Basically all it does is it states that any multiple of any prime number cannot be prime. And really this just helps to factor out what numbers couldn't possibly be prime, just leaving you with ones that could be prime. Then all you have to do is check those numbers and you'll have prime numbers. So yeah, it helps a lot. Okay, so now that you know that prime numbers are important but hard to find, you might want to know what I am going to try to do about that. Well, what I did in this experiment was I tried to make an equation to predict prime numbers. So this is what I did to do that. All right, so over here was my first step in this experiment. So really what I did here was I graphed the first 10, 100, 1,000, 10,000, and 100,000 prime numbers all on separate graphs. I then set linear trend lines to them in the form y is equal to mx, which is in all of these over here. And what I learned from these graphs was that, one, the relationship of prime numbers is not linear because these linear trend lines have to keep changing as you make the data sets larger. And then I also kind of the same thing, but I also learned that these slopes were constantly changing and getting larger, which meant that I had to predict the slopes. So this is what I did about that. So to predict those slopes, I graphed the slopes from all 5 graphs on this graph over here. And basically, I set a nonlinear trend line to it. right over here, and it was actually pretty accurate. It went through like it went through these pretty accurately. So yeah, basically what I did with this new information was I used it as a slope in a y is equal to mx trend line, because really at its core, this trend line is just predicting the slope of any of those linear trend lines. So you can just make it into y is equal to mx. And so that's what I did over here. Y is equal to the trend line and then all of that times x. And it basically just makes one of the trend lines from the previous slide, but with a predictive slope that just keeps adapting. Then after that, I wanted to test the accuracy of that equation. And so really what I did to do that was I predicted the first 10,000 prime numbers with that equation. I then saw how far off each of these predictions were, or the difference of those predictions, and I graphed them on this line right here. So what I learned from this graph was that my equation was very inaccurate. It just kept getting farther and, well, more and more inaccurate in the negative direction. It started guessing lower and lower than it should have been. But what I did see was that this was kind of like linear relationship with some deviations. So what I did was I set a linear trend line to it in the form y is equal to mx. And this is the trend line right here. Then what I did was I took that trend line over here. I multiplied it by -1 to get the opposite of basically the predicted difference. And I added that to my original equation. And so basically what that did was it predicted the difference, and then it took the opposite of that, and then it just put it right back onto my original equation. It added that to my original equation, which should basically just offset how far off my equation was at any point. So that's the main thing that was doing. And so with that new final equation, I wanted to test its accuracy. So I plotted that new equation's first 10,000 predictions, and on that same graph, I plotted the first 10,000 prime numbers. And as you can see, the prediction in orange and the prime numbers in blue are practically on top of each other, which shows that my equation is pretty accurate. Now, if you're not convinced by that, then you can look over here. This is essentially the same graph I showed you on the previous slide, but with the new equation. I predicted the first 10,000 prime numbers with that new equation, and I saw how far off each of those predictions were. I then graphed it over here, this time not setting a trend line to it, and I saw that it was still deviating quite a bit, but the main point was that it was deviating around 0. So it just kept going up and down and up and down around 0. So it had its points where it was pretty accurate and its points where it was pretty inaccurate. But the main point was every time it got inaccurate, it mostly just got back on track, which shows, again, that my equation was pretty accurate for tracking the general trend of prime numbers. If you're still not convinced by that, then you can look over here in this table. So basically, it shows the prime number rank, which is, I should probably just explain what that is. So the prime number rank is basically the number of any given prime number. So the easiest way to explain that is with an example. So the 10th prime number is 29. So its prime number rank would be 10. The 100th prime number is 541, so its prime number rank would be 100 over here. So yeah, that's basically what it is. And then over here is the actual prime number value, which I basically already explained. It's just, it's the prime number. The 10th prime number is 29, so this would be 29. The 100th prime number is 541, so its prime number value would be 541. So yeah, this table shows the prime number rank, the actual prime number value, what my final equation predicted for that prime number, and then how far off that prediction was. And then, of course, also the percent of that difference, calculated by dividing this over here by this over here. So yeah. Anyways, so really what this is showing in the difference is that my equation is not accurate. Because if you look at the difference, it's showing that this equation just gets farther and farther off till it's off by like over 82,000 at the millionth prime number. But if you look over here at the percent difference, you'll see that that just stays between -3% and 1%, like the whole time all the way up to 1,000,000, which shows for at least each of these checkpoints up to 1,000,000, my equation did a pretty good job just tracking the general trend of prime numbers in a way, I guess you could say. Yeah, just its difference kept getting farther off, but the percent difference, which really takes into account how large these numbers are getting, it's not actually that far off. The percent difference stays pretty low. And so, yeah, considering the large scale of the numbers that this equation is dealing with, this shows that it's actually pretty accurate for at least tracking the general trend of prime numbers. Maybe it doesn't predict them perfectly, but it does seem to track them, or their general trend, pretty well. Now, even though the final equation was pretty accurate for tracking the general trend of prime numbers, there were things that could be done to improve this experiment. One thing could be a better computer, because it could generate larger data sets, it could create graphs more effectively with those larger data sets, and it could possibly plot accurate trend lines more effectively and efficiently and more accurately on those graphs. This could just make the equation more accurate all around. Now, additionally, there were little blips and deviations in the data for my final equation, like its difference, and that's believed to, well, it was found during this experiment that huge swaths of data without prime numbers in them, and also prime number twins, which are two prime numbers as close together as possible, so like 3 and 5 are both prime numbers, and together they make a prime number twin. But anyway, so yeah, it's like large swaths of data without prime numbers in it, and prime number twins seem to just be little blips and deviations in the data, which just threw my equation off course. And so if there was a way to predict these strange little occurrences, then maybe it could make my equation more accurate, like with a fault equation or some other term or something. Then lastly, a real mathematician on the study team for this experiment could probably help with mostly the methodology of this experiment, to like make the methods for finding this equation more solid, more foolproof. So yeah, I can make the methodology better, or a mathematician could even improve the experiment by other means. Because really, this study team was made up of myself and my dad, and as of right now, neither of us are real mathematicians. So in conclusion, the equation found did pretty well with predicting the general trend of prime numbers. Maybe not predicting them accurately, but following the general trend of them. Now I would like to acknowledge a couple of people who helped a lot with this experiment. Firstly, I would like to give thanks to my father, Craig S. Nunemaker. He has helped tremendously with this project. In fact, I consider him to be part of the study team. The main things he did to help out were offering valuable input in the experiment and graphing on the platform of Excel, which was just better and more flexible than my graphing platform, Google Sheets. The input he offered, but was not limited to, creating figures 2 and 4 and helping with my various presentations, including this one. All of these efforts have truly contributed to this project. Thank you, Dad. So going back to this over here, creating figures 2 and 4, he did help tremendously with that. So basically, for figure 2, I knew I wanted to predict the slopes of those linear trend lines in figure 1, but I couldn't figure out how. I went down like this weird rabbit hole where I was using really complex methods to try to predict those slopes, and they did not work at all because I didn't really understand the methods I was using. So he eventually figured out that you can just graph them and use a nonlinear trend line. So yeah, he helped a lot with figure 2. And then for figure 4, he wanted to find a way to prove the accuracy of my equation, so he created figure 4 to help prove the accuracy of it. He also helped a little with table 1. Yeah. Then I would also like to give thanks to Sherry A. Beagleisen. She was my science fair teacher for this project, and so of course she helped to instruct me for just about every aspect of the project, and she also provided valuable input. She helped me from the choosing of my project, which my dad also helped with, to the submitting of it for district science fair. Thank you, Miss Beagleisen. And here are my sources. Thank you for your time.